Hi, this is Ms. Fitzmaurice, and this video is an introduction to banked curves. If you have not already done so, what I want you to do is first read the section in the book on banked curves and then come back to the video. Okay, if you've already read the section in the book, go ahead and watch this video. Okay, so when you are driving, or your parents are driving, and you're going on or off a highway ramp, usually, not always, the highway ramp has some kind of curve on it, okay? And most of the time, whether or not you notice it, so this is like a side view, the curve is going to be tilted, so that if this is your car, and you're heading like into the page, you are kind of at a diagonal. You know, your direction of motion can't be shown here. Okay, a top view would look something like this, and you are going around the curve, but the curve itself is tilted. So you're going this way, and the curve is tilted. So that you don't fly off the road, and unfortunately, if you've seen highway ramps that are curved, especially when highways are merging, you'll see a lot of tire tracks going into the side. You need to make sure you're not going too fast. Okay, so in this video, we're going to relate the angle of the curve, the speed you're going, so your tangential velocity, and the amount of friction between the tires of your car and the curve. Alright, so the first thing that we're going to deal with is if you had no friction, how fast could you go? Okay, so first of all, let's think about a non-banked curve. Okay, so your car is just driving around a flat surface. If your car has a certain tangential velocity, Vt, and there's no friction, so there's no friction pulling you inwards, your car is not going to keep going around in a circle. You're going to fly in the direction of your Vt. That's why highway curves are banked, because if there was rain or something like that, there's a bigger chance you would just go flying off to the side. Okay, now let's think about a banked curve. So again, this is a side view. Okay, so this is like the hill and the circle you're going around. You're kind of going around this way. I can't really draw it into the page. This is your car. Okay, so what I want you to do is take a moment and draw a force body diagram of what forces are acting on your car. Okay, so pause the video, draw that force body diagram. And now that you've drawn that force body diagram, you should have realized this is pretty much like the forces acting on something if it's just on a hill. So we have Fg down. We said no friction, so we don't even have to worry about the direction that friction might be pointing. And we have the normal force pointing straight up. Okay, so my first question is, what causes AC? What causes you to move around in a circle? And remember that if this is your bank, I'm going to draw, this is like the tarmac that I'm drawing, the center of the circle, the direction of the center of the circle is this direction. So maybe your center of your circle is over here. What causes you to accelerate in that direction? So looking at our force body diagram, I want you to decide which force is contributing to AC and write it down. Okay, so now that you've written it down, the answer is Fn. And in particular, it's Fnx. And you might be saying, but wait a second, in a hill problem, we draw x and y. Okay, so Fn doesn't have an x component. Actually, for a banked curve problem, we're going to keep our normal axes. So I'm going to write that down again, and you can write that down again, and we'll talk about the specifics of how we break these forces up. Okay, so again, this is not a regular hill problem. I cannot emphasize that enough. We have our car. Again, I'm going to draw a dotted line for my hill, and we know here's our car. The center of the circle is over here. It's going around in a circle. Maybe it won't make a complete circle, but its motion is now circular. Okay, so of course we have FG down and FN off to the side. Now my argument is that because AC, our net acceleration, is in this direction, the normal, quote-unquote, or usual x direction, not the hill x direction, we actually want to make that our x-axis. So I'm going to draw this dotted line for our x-axis. It's just the normal one, or the usual one. I keep saying normal, but I don't mean normal as in Fn. And then the usual y-axis, so the one that lines up for Fg, will be our y-axis. And what this does is it means that our acceleration is along one of our axes. Now let's say our hill has an angle theta. I need to take a moment to convince you that this angle right here is the same as this angle right here. Okay, and the way I'm going to do that is I'm going to draw in a bunch of triangles in green that have nothing to do with the forces. Okay, so these green lines I'm drawing are just to convince you that the angles are a certain way, but you need to ignore them when dealing with forces. So that's a triangle. Okay, let's call this angle right here star. Okay, if you notice, theta plus star have to be equal to 90. So this angle right here also has to be theta. Okay, here's another 90-degree angle. So this angle right here has to be star, okay, because theta plus star is 90. And then here's another 90-degree angle. And what that means is the angle between Fn and our y-axis has to be